So today I'm going to be talking about power in circuits. And when we talk about power, you actually already have a very good understanding of power, because when we talk about power, we're talking about the brightness of a bulb. So power in circuits is something that you have dealt with probably your whole life. When you go to the store to buy a light bulb, what are you buying? How do you decide which light bulb to buy? I mean, besides like LED, incandescent. You are looking for the brightness of the bulb, which is described as the watts that the bulb is in. So when we're talking about power, what we're talking about is the brightness of a bulb, and that is described by the watts, the wattage of that bulb. We have done two examples of circuits with multiple resistance bulbs. So if this has a high resistance and this has a low resistance, and they're in series, predict which one's going to be brighter. So think about it, pause if you need to, and remember that in series, the current is the same. So there's the same current going through this bulb as going through this bulb. Now, if they have the same current, do they have the same brightness? Well, no, because they have different voltages. So what would the voltage be like across these? All right, for the same current, a high resistance, remember that Ohm's law, V equals IR, high resistance, same, this would have a high voltage. Low resistance, this would have a low voltage. Same current, higher voltage. In series, the high resistance bulb is brighter. It has more power going to the bulb. The bulb is using more power from the circuit. Now in parallel, we have a high resistance bulb and a low resistance bulb. So if we have high and low, now remember that in parallel, the voltage is the same. So they both have the same voltage, the voltage of the battery. So if this is the voltage of the battery, it's the same here, same here. And now with this, if they have the same voltage, are they the same brightness? Well, no, because they have different currents. So here, if the voltage is the same, current is voltage divided by resistance. So voltage divided by a large number means a small current, and voltage divided by a small number is a large current. So that's if you think about it mathematically. If you think about it conceptually, there's a lot of resistance in this path. So there's not as much flow going through. Here, it's a much lower resistance path, so this one has a lot more flow. So in parallel, okay, voltage is the same. This one has a bigger current. The low resistance bulb has the brighter power. The more power, the bigger brightness. So how do we figure out what power is? Well, in this case, the brightness was related to voltage. In this case, it was related to current. And we're going to figure out that it's both. So the power is related to both current and voltage. And now there's a subtle difference in the equations that we use for power. For P equals IV, power equals current times voltage, this is technically the power given to a circuit by a battery, because a battery provides the voltage and provides a current. So this is the power that's provided to a circuit by a power source. But what these do, what resistors do, bulbs, resistors, they use up power. So the power used by a resistor, we can have two different forms of the equation. We can have it as current squared times resistance, or voltage squared divided by resistance. All three of these are mathematically equal because of Ohm's law. I'm not going to be too picky about which one you use, but I just want you to be aware that technically this is about the power given to a circuit by the battery or the power source. These are the power used by a resistor. So that's the basic idea of power and brightness. Now, the units of power, I said, well, you already know it. It's a watt. Yep, it's a watt. But what is a watt? So if we look at these three equations, that one, okay, so power is in watts, current is in amps, and voltage is in volt. All right, so a watt is an amp times a volt. Let's do this one. Okay, so a watt would equal current squared, okay, amps squared, times the resistance, times ohms. So that is also a definition for what a watt is. Third one, a watt is, let's see, V squared, so volts squared, divided by the resistance, volts squared over ohms. So what is a watt? It is one of these weird combination units where we don't know exactly what we're doing because it could be anything. You know, it could be any of these, and really a watt is any of those. So to get you a sense of how big a watt is, well, think about batteries. Think about bulbs. You know how much a 15-watt bulb would be. It's a very dim bulb. And a 100-watt bulb would be something that is rather bright. 150 watts, even brighter. And so a watt is just a measure of how much power is being used up by a resistor or how much power is being given to a circuit by a battery. A related concept is on your power bill. Now, we often talk about our bill from Xcel Energy as a power bill. Is it really power? If you think about the units on that, next time you get your utility bill, look at the unit. You are paying a certain amount for kilowatt hours of something, of utility something. A watt, kilowatt, watt, that's power. But this thing here is power times time. So what you're paying for when you pay your power bill isn't actually power. It is technically energy. You are paying for energy. And in first semester physics, we talked about energy often in terms of joules, but another unit of energy would be a kilowatt hour. So with kilowatt hours, we can figure out how much it costs to run certain circuits, to run our TV, to run our fridge, to run a light bulb, and then it's going to be based on figuring out how much energy we use and then the cost of that energy. So let's just do an example. How much would it cost for one 100-watt bulb? So just one 100-watt bulb. Let's say it's on for 12 hours a day, and we want to know how much it costs per week. And then if you go to your Xcel Energy bill and you look at the cost of energy, energy's cost is about 11 cents per kilowatt hour. So how much are you spending if you had a 100-watt bulb on for 12 hours a day for one whole week? One of the nice things about power and energy, these problems, is if you can get the units right, you will have the right answer. So if you just match up all your units, you'll be in great shape. There's no extra halves or twos or factors of 4 or squares or anything like that. So we want to know cost. So we want to know what the cost is. Well, that's dollars. All right, I have dollars here, but that's the cost per kilowatt hour, which means I need to know how many kilowatt hours that 100-watt bulb is using in 1 week. All right, so kilowatt hours, just look at the unit. We have kilowatts times hours. Well, I already know my watts, so 100 watts, I gotta convert that to kilowatts. So divide by 1,000 to get 0.1 kilowatts. And it's 12 hours a day, so my time is 12 hours. I can just multiply those two to get kilowatt hours. So 12 hours times 0.1 kilowatts, I use 1.2 kilowatt hours a day for this bulb. This bulb uses up 1.2 kilowatt hours a day. Now I'm going to multiply by 7 because I want the cost per week. So I'm going to take that times 7, and that'll be 8.4 kilowatt hours. And now you might look at the unit and say, what's going on here? This is for a day, and now this is for a week. So yeah, we do have to be careful. So we'll use 8.4 kilowatt hours of energy in a week, we know how much each one of those kilowatt hours costs. So I'm going to take 8.4 kilowatt hours times 11 cents per kilowatt hour. The unit up top and the unit on bottom cancel out, and 8.4 times 0.11 gets me about $1. It's just a little less than $1. So a 100-watt bulb that's on for 12 hours a day costs about $1 a week, $4 for a month. And so that's an example of how to do a power question where you just focus on the units. There's no real good straight up equation because I'm just making the units work. Well, how many kilowatt hours? Take watts times hours. How much cost? We'll take that kilowatt hour times the cost per kilowatt hour. So these tend to be pretty straightforward in terms of the math, if you can just make your units work. Another concept that I want you to be aware of is the idea of battery ratings. Batteries, we said, provide a constant voltage, and then depending upon what's hooked up to it, different currents for different circuits that it's hooked up to. And our little tiny AA or AAA batteries are 1.5 volts. But the big honkin' D-cell batteries that we used in lab are also 1.5 volts. Why would we have different sizes? Why do we need different sizes if they're both the same voltage? And this is the idea of the length of time that a battery is going to last. Batteries are given a certain rating. Besides their voltage, they're given a rating in amp hours. And what this tells you is how many hours the battery is going to last at such and such a current, so for so many amps. So if we do, let's do a circuit and figure everything out for a circuit using a whole bunch of stuff. Let's do that. So I'm going to have us look at just a single bulb circuit with a little battery, so one of the ones we were using with the D-cell batteries to light with a wire in lab. So just a little battery and a little bulb. All right, just a single bulb. 1.5 volts, so C or D-cell battery. And I'm going to say that it's a 6 ohm bulb. So the bulb itself has a resistance of 6 ohms. And when you're doing these, make sure you're using the right words, because you should get practice with mixing up, the unit and the variable. So if I have ohms, that must be resistance. So I'm going to talk about it has a 6 ohm resistance. It's just a good way to get used to the variables that we're talking about. So what can we figure out about this circuit? All right, well, I know that if there's 1.5 volts across the battery, there has to be 1.5 volts across the bulb. So the bulb has 1.5 volts potential difference across it. What else can I find out? Well, if I know the ohms, the resistance, and the volts, the voltage, I can use Ohm's law, V equals IR, to figure out, let's see, I have that one and that one, I can get the current. So current is volts over resistance, so 1.5 divided by 6, that's going to give me 1/4 of an amp. So I now know my current in amps is 0.25. How much power does this bulb use? It's not going to be a lot, I'm guessing, with a 6 ohm resistance. So now we can go to either one of these, or if you want, you can use this one, because mathematically it is the same. Technically, physically, this is better, but mathematically, you can use any of them. That one's the easiest because it doesn't have a square, so use whichever one you like. All three of these will give you the same power, and it would be good for you to pause right now and try it. Try all three. If I just use the basic one or any of them and calculate what my power is for this bulb, the power would be 0.375 watts. Okay, so if my battery has, let's just say, a rating of 3 amp hours. 3 amp hours. How long could it run the circuit? Okay, so how long would it run the circuit? I want time. If I look at all of my units here, there's the only thing that has time in it. So I have this 3 amp hour thing. And I don't know if that has an actual, if there's a certain variable. It's just the rating of a battery. It's amp hours. So if I want this, I need to know how many amps I would have. Well, I know how many amps I have. So I can just match up amps times hours. I have 0.25 amps times how many hours. So that'll give me amp hours, and this is another example where if you get the units right, you'll get the math right. So divide both sides by 0.25, that's 3 times 4, so my time is 12 hours. So a 3 amp hour battery at 1.5 volts would power a 6 ohm resistance bulb for 12 hours. So that's how we use the idea of the rating of the amp hour as well. So with power, all we're dealing with is just making the units work. We'll keep on using Ohm's law because that's valuable. And then we've got these different ideas for what power is, how to calculate power. There's the idea of the amp hour for battery ratings, and then there's the idea of a kilowatt hour. So if I were to bring this bulb into class, and let's say I forgot to turn it off, how much would I be spending if, let's say, I left it on for a whole day? Okay, so how much would I spend if I left this on for an entire day? All right. Well, okay, so I want my cost, which means I need to know how many kilowatt hours I'm using. All right, there's my watts. So kilowatts times hours. I need my kilowatts. Oh boy, this is a small number. You divide this by 1,000, so 0.0012375 kilowatts times the number of hours. I said it would be 1 day, 24 hours. And that'll give me my number of kilowatt hours used. And then I would just take my cost per kilowatt hour times the kilowatt hours, and that'll give me my total cost for leaving this thing on for a whole day. And I don't have my calculator here, so I'm going to trust you to get the answer on this one. It's not going to be very much. As I said before, the cost per kilowatt hour is somewhere around 11 or 12 cents per kilowatt hour, so you can figure that one out. But this is an example of a power problem, doing all sorts of calculations with a basic power problem. People tend to do really well on this one, and if you need more help, there's always time to come talk to me in office hours. Otherwise, you can just play around. There's plenty of practice problems online. I can get you more practice problems. Other than that, I think we've covered everything I need to cover. All right, good job.